right, we might as well get started. Good morning, everyone. I hope you enjoyed the dinner at the museum last night. There was no wine left in the end, so I didn't have to drink any. Well done. We have our second keynote for this conference now, so we're very fortunate to have Marshall here. Just recently taken over as maintainer of lib C++. It's also on the C++ standards committee. So you can thank him for C++ 11. He's going to speak to us today about what's new in C++ 14, so the next edition of the standard, right?
Right.
Marshall.
All right, thank you. Good morning, everybody. Hopefully we're all recovered from last night. So I'm going to talk about C++ 14 and what's new in it, what the changes were, why the changes were made, and how you can take advantage of it. So we'll start with what has been called C++ 1Y for a long time. Originally in C++, what became C++ 11 had a code name of C++ OX because nobody knew what year it was going to be released, but everybody was sure it was going to be released in the 2000s. And then came 2009 and 2010. And people on the committee just said, oh yeah, OX, that means hexadecimal. Don't worry about it. And it became 2011. And in 2000, it became 2011, it became C++ 11, and so the next standard we just dubbed 1Y. It's going to be in the teens somewhere, we don't know where, and it's almost certainly going to be 14. So a little bit of ISO acronym snuck into my slides here. The DIS up here stands for Draft Internet Standard. And that is basically when the standards committee says, we think we're done, okay? There's no more to go in. We think it's happy. Now, send it out to all the national bodies who make up the ISO, and they comment on it. And they send back a bunch of comments, and then the committee will respond to the comments. And the committee has to actually respond to every single comment, but sometimes the answer is no. But the committee says, a national body will say, oh, you need to change this, and the committee will say, no. Or more commonly, they'll say, there was no consensus on the committee to make this change. But okay, this all happened in the Chicago meeting, which was in October. And then the comments were all gathered, and the committee met again in February in Issaquah, outside of Seattle. And we addressed all the comments, and the changes that were made in Issaquah were merged into the working document, and this was voted out as the final draft internet standard. And at this point, it's sent out to the member nations of the ISO. The national bodies now have 5 months to look at it, to study it, to do whatever they want, and then come back with a yes or a no. And the expectation is that enough of them will vote yes, that the FDIS will become actually the international standard that ISO will publish, and that will become C++ 14. The voting period ends in mid-August, and we won't know for sure till then, but basically everybody is working under the assumption that it will be approved and it will become C++ 14. Okay? Any questions about this? If you have questions about any of this at any time, just put your hand up, okay? Don't save your questions for the end of the talk because, well, you're liable to forget them, or I'm liable to forget them. Okay, C++ 14, how did we get here? A little bit of history. We had C++ 98, a long time ago. C++ 03 was just a couple bug fixes. I mean, the one that I remember was that there was a requirement added for vector that all its storage be contiguous, which everybody did, but now you could depend on it. So really not much going on between 98 and say 2005 and so on. It was C++ was pretty much unchanging. We started a series of technical reports in the mid-2000s, of which TR1 was really the only one that went anywhere. And then, there was all this I guess, pent-up energy behind C++, and we got to C++ 11. And boom, there's this huge list of new features and new capabilities in the language. This is not all of them, but this is what would fit on a slide. But there's an entire threading infrastructure there, and an entire a definition of a memory model. What users see is range-based for loops. They're really cool. They were one of the minor features. Auto, lambdas, R-value references and move semantics. This whole idea that sometimes it's easier to just steal the guts out of an object and put it over here rather than make a copy of it and then deallocate the original or free the original. Variadic templates and tuples, or as I like to call a tuple is pair with a completeness fetish. Why 2? Why not 3? Why not 4? Why not a million? User-defined literals, regular expressions. Every language in the world has regular expressions, and now so does C++. Uniform initialization, which is not as uniform as everybody might like, but it's way better than what we had before. The unordered containers. These were in TR1. Now they're in the standard. Stud chrono. Great facility for timing things, for calculating time-based things. It's this amazing bit of infrastructure that is necessary actually for the threading, but it's useful in and of itself. And const_expr, the idea that you can do calculations at compile time and use the results as compile time constants, like the size of an array, say. All these things showed up in C++ 11. This huge pile of new features. C++ 14, on the other hand, much more focused, a much smaller release. Okay, it basically had three goals. There was fix some bugs. Okay, fix some bugs that people had found in the specification for C++ 11. Take some of these new features that we introduced in C++ 11 and say, these are nice, but they're not really complete. There's more you can do here. And so I put that under fleshing out some of the features. And there were a few new features in C++. There are a few new features in C++ 14. It's kind of funny to speak of it in the past tense. So we didn't put out a release with no new features because this is software. You can't do that. So fleshing out, 3 main areas: const_expr and tuples, and just the idea of make whatever. I'll get to that. But const_expr in C++ 11 was very limited. You could have functions that were const_expr. They were pretty much limited to a single return statement, which led to really interesting convolutions with the question-mark:: operator, where you could build a whole if-then-else tree with lots of with lots of decisions along the way by by nesting this. But that was really hard to read. It was hard to get right. You look at it and say, what? And and it was really limiting. And there was people wanted to do more. People wanted to do a lot more. And so there are much looser rules on const_expr. You can actually have variables. You can have loops. You can have ifs and so on. And people are using this for really quite impressive things. I have not yet seen an implementation of, say, a sorting algorithm all written at const_expr time, but it wouldn't surprise me at all to discover that you can do that. The things you still can't do, you can't really use pointers. Okay, you can if they are, say, global variables, because the compiler can have an idea what the address of a global variable is at compile time, or it can make a reference to that. But local variables, for example, you can't take the address of, because who knows what they're going to be at compile time. Anyway, so constexpr, much more capable in C++ 14. I've seen people building, building hash tables at compile time, or things like that. Anyway, tuple. Tuple was new in C++ 11. It works really well with variadic templates. I mean, you have to have variadic templates to do tuples, really. If you go back to boost tuple from, before C++ 11, it was all done with just stamping out templates. One with one parameter, one with two parameters, one with 3, 4, 5, 6, 7, 8, 9, 10. And it was just a mess. Much easier to use than to develop, but still, it was a mess. So what can you do with this? The first one is, everybody says, get. Fine. I like to get the elements. I want to get the 0th element, first element, second element, and so on. But now you can actually get them by type as well. You can say, get me the string out of the tuple. Get me the int out of this tuple. Get me the complex double out of the tuple. Get me the user-defined type out of the tuple. And if the tuple doesn't have one of those, or it has more than one, this is a compile time error. Just like if you say, get me the 7th element out of this tuple, and the tuple only has 5 elements, compile time error. Compile time integer sequences. Has anybody used these? Just show of hands. Okay, a couple people. Yeah, of course you have, Richard. Richard, yeah. I implemented these for libc++, and then Richard rewrote them. But anyway, compile time integer sequences are this really cool thing for template metaprogramming because you can, because get, the get that pulls things out of tuples will take a sequence of integers through the expansion of parameter packs. And so this is a facility for building sequences of integers that you can use with get and so on. And so you can slice and dice tuples however you want. You can, if you say, I want the Fibonacci indexes of a tuple. I want the first one, I want a new tuple, which is the first one, the second one, the third one, the fifth one, the 8th one out of this tuple. Okay. You build an integer sequence, which you can do at compile time, of the Fibonacci sequence, and then you say get that sequence out of the tuple, and you get a new one with those elements. You can reverse them. You can just the odd numbered ones, the even numbered ones, and this is really useful in in very generic programming when you want to basically slice and dice your data sets. I suspect that people writing database interfaces are going to use this an awful lot. One of the things that we saw in C++ 11 was a couple functions that just start off with make whatever. Make move iterator, for example, or make shared. Make shared is a really nice thing for making shared pointers. It has a couple advantages. The first advantage is that over doing it yourself, the first advantage is that it's efficient memory-wise. It allocates the control block and the thing that it points to all together in one block. So you have one block on the heap instead of 2. And in C++ 14, we started adding more of these make whatever features, or functions. Some of them actually have performance advantages or efficiency advantages. Others of them don't. They just have their convenience functions. The idea is that you don't need to know that, for example, that whether or not make unique actually has a performance advantage to you. You just know that the best way to make a unique pointer is called make unique with a set of parameters. If it turns out to be the same as doing it yourself, well, that's OK. You don't need to remember that, or make shared, or make reverse iterator. And you should expect to see more of these in a future version of the standard. OK, new features in C++ 14. This is not all of them, but this is a sampling of them. I'll go through most of them. But again, a small list compared to C++ 11. polymorphic lambdas. As soon as people started writing lambdas in templates, they asked us, so can I have a lambda with an auto parameter type? Because I don't know what the parameter type is in my template. It's a template parameter. And this turned out to be like the most requested feature about lambdas once people started using them. If you think about how this is implemented, right? When you write a lambda, really what happens is this struct gets created with a procedure call operator that is a function that contains this. And the capture variables are member variables of that unnamed function, unnamed struct that gets created. Well, for this kind of thing, you end up with a templated procedure call operator. But you just write AutoX and the world works for you. So this is, if you wanted to call findIf and you inside a template and you didn't know what type you were, so you could just say this and say find this value in whatever and pass that as a predicate or whatever you're looking for. Variable templates. You can template functions, you can template classes, you can template structs. Now you can template variables. You can have, this is a template which lets you stamp out, a bunch of variables of different types, all with the same name. So you can refer to a variable here as pi, open bracket, long double. And you get a long double with this value to whatever precision your long double matches. And you can, T can be your type. It doesn't have to be a built-in type. As long as your built-in type can take this kind of parameter in its constructor. Digit separators. People wanted this for a long time. Everybody said, really? Yes, we really, really want this. And there was this huge, long debate on the committee going on for several meetings about what's the best way to do this and so on. And a lot of people wanted underscores, okay? But Doug Greger demonstrated in a meeting that underscores didn't play well with user-defined suffixes at all. And he had a nice chart with an example, or just boom, boom, with using underscores with a bunch of things that looked exactly analogous, and you get wildly different results. And so everybody agreed that underscores just weren't the way to go. And so we settled on single quotes. This is actually supposed to be a single quote, not a backtick. But my presentation software decided to smart quotes it. Anyway, so you can now write your numbers here that are easy to understand, easy to read by eye, and say, okay, that's 9 digits, not 10 or 8 or 11 or whatever. Notice that this is just for literals. This is not, ATOI. If you pass, ATOI this string, it won't actually parse it, say, or if you take that, if you try put this in a stir stream and try to read it into an integer, that won't do it. It's just for literals. If you try to read this sequence of characters into an int, from a stream using the stream extractor stuff, you'll get 1, 2, 3. You'll get 123. You won't get 123 million whatever. Binary literals. You could specify bit patterns directly, which for people writing low-level code, they really like that. Well, Kostya says, oh yeah. Kostya's switching his entire development system over to C++ 14 in counting in 3, 2, 1, done. Because you could write 74 here, or you could write, whatever that is in hex, 64 plus 10. But if you really want bits, you should be able to specify bits. Heterogeneous lookup in containers. This actually was a bug fix that people wanted for the standard library, and it turns out to affect all sorts of things, every single container and a bunch of the comparators. So if you have a map, which is a string mapping to something, doesn't really matter what, and you say, find me ABC in that map, what does it do in C++11? It constructs a temporary string with the contents ABC and uses that for the lookup, because string is the key type of the map. This is kind of silly, because std string knows how to compare itself to a char pointer, a null terminated string, to a char star. Why construct a temporary string? So now, if your comparator function meets certain criteria, in particular if it has this magic type def that says I can do transparent lookups, now the find or the lookup operations on various containers is now a template function, and it will take the type unchanged and use that as the lookup rather than constructing a temporary. If you're doing a lot of this, this is a huge win. If your key type is very expensive to construct, this is a big win. Another one which might be considered a bug, but it also might be a new feature, quoted strings. So what happens if you do this? You have a string, hello world, and a stir stream, and you write it out, and then you try to read it back in. And you say, oh, is it the same string? It's not, right? Because the extractor for string reads up to the first white space. And y will be hello. Okay? There's good reasons for this. It's been this way for 15 years, since C++98 and before. But in many cases, that's not actually what you want. And so the standard library now has a new facility called quoted. If you say, write out a quoted version of this string, read it back in, and compare it, and you know what? Now it's the same. And so if this is the behavior you want, you now have a facility for this. Excuse me. What this really does is it writes out a double quote, followed by hello world and another quote. And there are knobs you can twist to say, no, that's not the delimiter I want, and so on and so forth. But the basic idea is that you get back what you wrote out if you're dealing with strings, and you don't have to worry about whether or not there are spaces in them or new lines or whatever. OK, fixing things. There were three basic things that you can that we did in the standard for C++14. We fixed some bad specifications. There were a couple places in the standard, mostly in the library, where things were specified in such a way that it was impossible to implement them in a thread-safe manner or in a way that didn't leave dangling references. So we fixed some of those. Somehow along the way, the strong exception guarantee for vector pushback got broken with the introduction of R-value references in like a couple very much edge cases. And so we spent an awful lot of time talking about this. And also, there were several places where the standard decided to disallow temporaries because this leads to unsafe code. And so there are a few places where if you wrote a particular chunk of code, that it will compile in C++11 and be rejected by a C++14 compiler. So let's talk about that a little bit. Disallowing temporaries. For some places in the library, will return references into containers. And this is a problem if the container is a temporary. And actually, we're going to see more of this if the ranges study group ever comes back and starts proposing a lot of range algorithms. There's a lot of interest in that. But this is a general problem. Here's an example. Okay, we have a function that returns a string. We have a regex that searches in a string. We say match the string returned by this function here, and we're going to do something with the results of the regex match. The problem is that M1 is a regex submatch, and it's really a pair of iterators down inside. Okay, it's an iterator into what? Oh, into this string. But that's temporary. And right here, it's gone. It gets deallocated. Okay, and so now you have iterators into a string which has been destroyed, and who knows, maybe the storage on the stack or whatever has been reused. Certainly the storage on the, if this is a string that doesn't fit into the small space optimization, the storage on the heap is gone. And so this is actually really easy to write in C++11. And it doesn't work at all, or maybe it works. You're reading deallocated memory. If you're running ASAN, on the other hand, ASAN will tell you, no, don't do that. But in C++14, the version of regex match here, there's an additional overload that takes an R value reference to a string and is marked as deleted. And so if you try to compile this, you will get a compile time error. It says attempt to call a deleted function. We thought that this was much better than silently failing at runtime, or maybe spectacularly failing at runtime. You never quite know, or getting the wrong answer. So any questions about this? Because you probably will see more of this as well. OK, status of implementations. We have C++ 03, 11, 14. We have 3 different C++ standards. Okay, C++ 98 took a long time, or 03 took a long time to implement. I don't know what was the first compiler that actually had full C++ 98 compliance. EDG. EDG? Yeah. But EDG isn't a compiler. It's just a front end. Yeah. Yeah, but no, I mean something I can build my programs with. Okay. I know that GCC 3.4, which was released in 2005, the release notes say we have much better. We have almost full compliance with the standard. Or no, they said we're much closer to the standard in 3.4. Okay. But that's like 7 years after C++ 98. And then they did, and I looked through the rest of the release notes, and they didn't ever say, oh yeah, we're fully compliant now. And yeah, you can argue that that nobody ever implemented the full C++ standard because of export templates, again, except for EDG. But no, I mean, it took a long time. 7 years after C++ 98, I don't think there were any shipping compilers that had a complete implementation.
There were compilers that were built using EDG
to
do translation to C,
and
those ones were being deployed.
Okay.
But they too lagged the actual standard. It would have been about 2001 before they did 98.
Oh well, that's better than a bunch of the commercial compilers.
And they were also extremely significant in discovering bugs in the template description.
Yes.
They were trying it out to find it doesn't work.
Yes, I mean that's one of the things that having implementations of things before they go in the standard is a huge win, because then you have some confidence that the people writing the standard aren't just blowing smoke.
Yeah, and Jason Merrill on the GCC compiler used to be sitting in committee trying it out, and he'd add to the compiler in real time. So that won't work.
Yeah, that won't work. That's a handy thing to have. C++ 98 took a long time, and there were compilers, as you say, early on, 3 or 4 years afterwards, but in widespread use or in commercial, how do I say this? Things like Visual Studio GCC, the Sun compiler, Sun CC or IBM CC or whatever. Yeah, it was easily 5, 6, 7 years before you could get.
Mainstream.
Before it was mainstream. Thank you. C++ 11 implementations are ongoing, and so are C++ 14. So C++ 11 implementations, we have Clang and libc++. Okay, before I go farther than this, I have to make a point that really when I talk about standards conformance, there's two halves to it. There's the compiler, and there's the standard library implementation. And they tend to be kind of independent. One can implement the full language, and one can be missing pieces out of the standard library. Or the other way around, somebody can implement the entire standard library, but maybe your compiler is missing a feature or two. So anyway, so in Clang 3.3, last June, we had a full C++ 11 implementation, 2 years after the standard shipped. GCC shipped full language implementation in 4.8.1, which was May 2012, just before Clang 3.3 was released. And libstdc++ will implement the full standard in the 4.9 release, which is any day now. No. They tend to release things around April. I haven't heard anybody setting a release date. What? They haven't made the branch yet? OK, so it might be a little longer than any day now. But anyway, really soon. Visual Studio Visual C++ has been implementing pieces of both C++ and 11 kind of concurrently. And Oracle shipped a beta compiler with limited C++ support last week. And if you go look at the release notes, you realize that they weren't kidding about limited. There's lots of things that compiler doesn't do yet. And without slagging on Oracle, when I saw the release, I looked at it and I looked at the calendar and I said, are we back in 2012? And I actually don't know the status of, say, ICC or IBM's compiler, although I know there's a lightning talk about Intel's compiler efforts later today. So hopefully I will be enlightened. C++ 14. So in Clang 3.4, I'm deliberately all you people who worked on Clang and LLVM and libc++, shipped a complete C++1y implementation in January. Okay, I say C++1y instead of 14 because this matched the FDIS that was voted out in, not the FDIS, the draft internet standard that was voted out in Chicago in October. Okay, whenever the next Clang release, LLVM release 3.5 is out, which maybe June, I don't know. I don't think we've set a date for that either. We will have a complete C++ 14 implementation. And the difference here is all the changes that were made between the draft internet standard and the final draft internet standard, which actually were surprisingly many. GCC and libstdc++ have some C++ 14 features in 4.8. They'll have more in 4.9, but it won't be complete. It won't actually be, there will be several features that are just not there. And as far as I can tell, they haven't started implementing. One of them is the extended const_expr rules. Visual Studio, I had a little note that said more on that later. They're implementing they're treating C++ 11 and C++ 14 as two halves of the same thing. They're saying, well, C++ 14 is a minor bug fix update to C++ 11. We're doing them together. And basically, they're just picking off features, and they don't seem to care whether it's part of C++ 11 or C++ 14. They're implementing them together. And they're rolling out these features. They have, every few months, they have a technology preview release of their compiler, which implements more of the upcoming standard, of the combined standards. Any questions on this? You can go out and start writing C++ 14 code today if you're willing to use. If you use Clang 3.4, you can get almost final C++ 14 compliance. Excuse me, and if you're willing to build your own Clang, you can have Basically, you can have a full set of C++ 14 tools today. Or you can wait a couple months until there's an official release. What's next? What's next for the C++ standard? Yeah, what the heck is a TS? So we had back in 2005 or so, we had TR1. And this was a technical report 1. It's a non-normative, which means it's not an official standard document put out by the committee that says, here are some extensions to the standard library that we've been working on that we think are going to be in a future version of the standard, and we would like people to be able to use these before the next version of the standard. Okay? The ISO, being this extra governmental agency, likes to rename things on a regular basis. You could argue that that's so nobody could figure out what they're doing, or because they come up with better names, or because somebody said, no, we're using TR for something else. It doesn't really matter. Now they're called technical specifications instead of technical reports. But in general, they're the same. Okay, there are details in the whole process thing, but in general, they're the same. They're things that the Standards Committee and the ISO will publish. It says, okay, here's a specification for a chunk of technology. It's not an official standard, but it's put out by the ISO. And we expect that some or most of this will show up in a future version of the standard. Now, out of TR1, if you remember right, almost all of that ended up in C++ 11. About the only thing that didn't was the special math functions. But there are a lot of technical specifications being written right now. People are working on them. The big one that's the farthest along is called file system. There's a file system library. It's based on Boost file system. The author is Beeman Dawes. And it's a way for dealing with file systems as opposed to just files. Iterating directories and traversing and all the things you would want out of a file system library. A mechanism for manipulating paths and locations of files and so on. There's an extension being written on array extensions, and really what that means is arrays of runtime bound. There's a couple ways to do this. One of them is just to extend the whole variable length arrays that GCC has implemented on the stack. There's also a proposal for a thing called DynArray, which is a real C++ object. The motivation for this is that in C++ 11 and beyond, we have a threading architecture, right? If you have a shared resource, to prevent data races, you need to protect it with a mutex. The heap is a shared resource. And so allocating things on the heap can be expensive in multi-threaded operations, multi-threaded systems, because you have to worry about contention. I mean, allocating on the heap is expensive anyway compared to allocating on the stack, right? Allocating on the stack is one instruction. Anyway, so there's a lot of interest in people writing high-performance code for having array-like objects, in particular arrays whose bounds are not known until runtime on the stack. If you don't care that they're on the stack, the answer is the same answer you always do. You get when you want a container vector. Array extensions, parallelisms, concepts. There's a concepts proposal. We're looking into it, and the nice thing about this concepts proposal, it's a little less ambitious than the one that didn't make it into C++ 11. And also there's an implementation of it. And so people are actually getting implementation experience and figuring out how it works. Modules is a new model for separate compilation to solve a lot of problems. I suggest that if you want to know an awful lot about it, you can either read the papers or you can ask Richard here, who is probably the expert on it these days. Okay. There are a bunch of committee study groups studying various things about possible directions. I mentioned ranges earlier. There's a lot of interest in algorithms that work on just ranges as opposed to pair of iterators, because you can do a lot of interesting things with them. You can compose them. You can manipulate them and so on. And there are people, there are people studying this. Networking. There's a study group looking into a way to have a nice native networking library for C++. And the same with reflection. Basically, people have wanted forever to be able to inspect structs and classes and say, how many members they have, what's the type of the second member, and so on. And people are looking into that. I mean, if you really want to do serialization of things, write objects out to disk, write things back in a general manner, you have to be able to know something about or actually have to be able to find out, about the objects. All the serialization things that I've seen right now involve actually intrusive methods where you have to write a serialization method for each of your classes. Okay, wrapping up. For a long time, C++ was a static, if you'll excuse the pun, a static language. It didn't change very much. There was a little bit of work on the TSs, but not anymore. C++ is come roaring back in terms of changes. There's a lot of interest in C++. C++ 11 has really, really kicked up the amount of interest in C++. There are lots of people doing research on C++, and Clang and LLVM are driving a lot of that, because now if you want to do work on research on C++ language issues, you can pick up a front end and start using it. Today, you don't have to spend 2.5 years, 3 years, whatever it is, writing your own front end so that before you can actually start your research. Or you don't have to go and license something from EDG, which means you can't then open source your research, or the results of your research, I should say. And the goal of the committee is really to make C++ a better language without sacrificing the things that people really like about C++. Generality, portability, performance. People are very concerned about performance in C++. The whole financial trading industry, at least in the US, lives and dies on C++, and they're very, very serious about performance. It's like, if I can make my trade 3 milliseconds faster than the guy down the street, I can make money. But a lot of this is being driven by Clang, LLVM, tools based on Clang and LLVM, based on the work that you guys are doing. And that's a great thing. There's a lot of stuff going on. Okay. Questions?
All right, let's thank our speaker.
Thank you.
Okay, one question at the back there. This is where my morning workout starts.
There you go. Up and down the steps.
Thank you. I want to add a small note on Intel compiler, because what Olka mentioned, Lightning Talk is actually a poster and on something different. So Intel compiler is based on EDG frontend. So you can speak about it, what you say on EDG, and full support of C++ 11 is available in beta version of next release, which is available now.
Is that language and library, or just the language?
Intel compiler relies on library that is available in the operating system. So on Linux, this is libstd C++. On OS X, it is libc++.
Okay, thank you. I don't know if everybody heard that, but yeah, the Intel compiler will be fully C++ compliant in the next release. Great.
Any more questions?
We got Kostya down here.
Back to the slide where you pass a temporary to whatever. Yeah, regex. So in library, we now support detecting these bugs. But what about user code? Do we have any method in the language to avoid this kind of thing in user code?
Yes, well, I mean that's what we're doing in C++ 14. If you do this, if you try to compile this in C++ 14, it will fail to compile.
I mean in user libraries, not not regex, but my own foo.
Is there the the technique that is used in the library is to regex match is to add an additional overload to regex match that takes an R value string and then mark that as deleted. Okay, there's nothing special in the compiler to handle this. It's all done in the library. So, so you can do the same thing in your libraries, but you have to say, oh, this is dangerous if you pass a temporary here. It requires work on the part of the library author.
We need to promote this feature as much as possible.
I agree. I mean, the earlier you can find, I mean, a point of principle with me is the earlier you can find bugs, the better it is. Finding bugs at compile time is way better than finding them at link time, is way better than finding them at runtime. It's better not to write them at all, but I'm not that good. So yeah, you can do this in C++11 as well. You can write libraries like this. We have something here, and you say, I don't want a temporary string, right, as this parameter. Make an overload that takes an R value reference and mark it as deleted.
Just one question. I'm wondering, what's the status on validation suites for C++14 and the libraries?
I see a hand down here. I do not know.
Yeah.
I know that libc++ has a pretty extensive validation suite, or test suite, I guess is better. It's actually what it is. It's not formally a validation suite. And that the people at Microsoft are using it to check their standard library implementation as well. But if you mean like commercial ones from...
Yeah, like Plum Hall.
I have no idea.
Okay.
I can't remember seeing an email from Plum Hall about the 14th
Plum Hall supports C++11, but not 14 yet.
There's a definitive answer for you. You had a hand up down here? Guess not. Was that a language validation or a library validation?
The one I was looking at was their language validation. I'm trying to see what their library validation actually says. I don't actually have any information about their library validation.
All right, thank you. Anybody else?
So speaking from the game industry point of view, the game industry tends not to use the standard library very much because they're a little more cautious about performance than the finance industry is, for example. And particularly memory allocation tends to be one reason why people don't tend to use the standard library, where they could write allocators. Have you listened to some of the concerns of the game industry to try to address some of those issues in the standard library?
The best way to have your to have a particular set of issues addressed is to come to a committee meeting and talk to people. Yes. But I don't remember anybody from the gaming industry specifically coming to committee meetings to talk. I know that the financial industry, for example, like Bloomberg and so on, and DRW and Morgan Stanley, they send representatives to the meetings on a regular basis.
Yes, I think it's been a bit of a catch-22 situation that no one's come because no one's using it.
Yeah, what was I going to say? The use of allocators is pretty much complete through the standard library these days, and so if you have you can, in fact, for example, there is a scoped allocator where you can allocate a block of memory, say, on the stack even, and say use this block of memory and do sub-allocations within that.
Yes, one of the issues we particularly had with a lot of our games was non-pod VLAs not being supported in LLVM, for example.
Right, non-pod VLAs, yes. Well, that's kind of the point of the array extensions TS, technical specification, is to standardize that and take it from being some kind of GCC specific extension to something that basically you will have on every compiler.
Okay, well, I shall go and evangelize it for you.
There you go. Yeah, and I just want to say that that there are some things you can do to get involved in the standards process if that's something you want to do. I mean, showing up at meetings. It's best if you don't just show up. You send a message to whoever the host is, letting them know that you're going to be there. You can, if there's things that you think are wrong in the standard, and it's a 1,500-page document, it's going to have bugs in it. You can file defect reports against it. You can offer suggestions. People write papers proposing changes to the standard, although really, if you write a paper proposing something, you need to show it up at a committee meeting and present it and defend it, or find somebody on the committee to present it and defend it, because otherwise it's not going to go very far. But yeah, it's not some secret cabal that meets in an undisclosed location at undisclosed times and nobody else is welcome. That's just not the case.
Anecdotally, the binary constants, that exact syntax and form was proposed in 1990.
I believe you.
And I have no idea why it was rejected.
There are some, yeah. I don't know either. I was not on the committee in 1990. I was not on the committee in 2000 or 2005. There.
Hi there. The functionality of concepts that was dropped from C++ 11 and brought into 14 you mentioned, is that similar to the C# concepts, or is this something totally different?
I'm not familiar enough with the C# concepts to actually give a good answer to that. It's not actually part of C++ 14. It's a specification that is being worked on with the goal of, if it's successful, it will go into a standard sometime after 14.
Oh, okay.
But it's not part of the current standard.
But is the purpose to make errors more understandable, or does it add more functionality?
Well, it's not just errors. It's more checking of things. Rather, the idea is be able to say, you're trying to instantiate this template with this type, and it requires these capabilities from this type, and you're not giving those, and so this type doesn't do that. And yeah, some of it is good error reporting. Some of it is just taking stuff that otherwise would compile and then fail at runtime and say, no, you need to do more here.
Okay. Yeah.
But if you go to isocpp.org, which is a website run by mostly by the committee, you can look at the papers there and you can follow the progress of the study groups and so on.
Thanks.
No problem.
Okay, one final question. Yeah. Okay. Well, let's thank Marshall again.
Thank you.